Okay, great. So many thanks for the invitation to speak in the seminar. So I'm Nicolas Boullé. I'm a new lecturer in the Department of Mathematics. So I joined about a month ago. And I'm working in the broad area of scientific machine learning and operator learning. And today I want to give you like a broad overview of the field and the new developments that we have seen in the past few years. So as I said, I'm working in the broad field of called scientific machine learning, which is a relatively new area. So the intersection between numerical analysis and machine learning, where researchers are trying to combine techniques for working with partial differential equations, so mathematical models that have been developed in the past 30 or 40 years in numerical analysis for solving equations or discretizing them, as well as incorporating the new machine learning models like deep learning that recently came, to incorporate the vast amount of data available. So you want to combine both rigorous numerical techniques and machine learning for working with large amount of data to make scientific discoveries. And so there have been several applications of this field. So in areas like weather forecasting, where the team at DeepMind incorporated both weather forecasting mathematical models along with historical data regarding the weather to given state of the weather at different snapshots in time, try to predict what will be the weather in 3 hours, 6 hours, 9 hours. There have also been some work on the protein folding problem that you may have heard of by another team at DeepMind, as well as materials discovery, and something that is closer to my own interest, which is on numerical simulations, where this paper by Resi Adani and Kanadakis in 2020 showed that you can actually simulate partial differential equations using neural networks, just having some partial knowledge on the model following the boundary and on the as well as data inside this domain. And so, in my opinion, there are three distinct areas in the field of scientific machine learning that you may be interested in, depending on what kind of problems you want to address, how much data you have available, and what kind of techniques you're interested in. So, for instance, if we are on this side of this triangle, here we assume that we have a small amount of data, so we don't have much measurements regarding our physical systems, but we have lots of prior physics knowledge. And so this is the area which I would call PDE solver, where in this case, our aim is given a partial differential equation, so a mathematical model that governs our systems, our physical systems, that governs our experiments, for instance. We want to compute the solution to this problem using a neural network. And so the idea is that you have partial differential equation like this form, which your model, is satisfied by your model. You don't have much data or much measurements regarding your system. And then you try to fix a neural network by minimizing the residual of this equation at certain points in the domain. And so a key advantage that if you already know your equation over standard numerical solvers, this is very easy to implement. You can also embed it into downstream applications. So if you want to do optimizations on top of it, this could be difficult to do with legacy numerical solvers, but could be quite easy to use to do with physics-informed neural networks. And some papers argue that this might work better for high-dimensional problems than existing approaches. But again, this kind of techniques is only applicable where you already know your equations. So in this case, there are also alternatives in numerical analysis using standard numerical solvers like finite element method or spectral methods. The second part, this triangle on the top here, is the area of inverse problems where we have some amount of data regarding our system and some amount of physics knowledge. So in this case, we may have access to, for instance, a dictionary of terms in your equations. So we might know that I have the equation that governs the system. I know that there are terms like the velocity that appear or UX du dt, etc., etc. So we might know some terms that appear, so some dictionary, the dictionary of functions that appear in the partial differential equations, but in this case, we might not know the coefficients on top of it. And so in this case, we might be interested in discovering the coefficients in front of this dictionary of terms. So we have a stronger prior of the physics that govern this system. But on the other side, we also have extra amount of data for which we can fit our model. And so this is what I call PD discovery, where so there's a famous technique called SIMD, so it's called sparse identification of nonlinear dynamics, pioneered by Steve Brunton and Nathan Kutz in the University of Washington, where they apply these techniques to dynamical systems, like one system here, and they try, given that they know that there are terms like here that appear in the model, so like 1x, y, xy, etc. They try to fit coefficients in front of these terms to discover the true form of the partial differential equations of the dynamical system. And so they use techniques based on sparse regulations, so kind of least square solver with additional regularization to enforce sparsity in the system. So essentially, they want to enforce that a lot of these coefficients here in front of these terms are close to zero. To discover a model that is a small model, a reduced model that is meaningful and interpretable. And using these optimization techniques, they are able to identify the correct dynamical systems for instance, Lorentz equations or other applications. There are also other techniques based on symbolic discovery algorithms by Tegmark and other authors as well. And so I'm focusing on the later area, which we call operator learning, where in this case we have a lot of prior physics data regarding our systems, but we almost have no physics information. So the idea is that you don't know what your partial differential equation is, you don't know what the model is. You have lots of data in the form of source, terms, and solution. So typically you might have, for instance, your solution at a given time t, and try to forecast the solution of your system at t plus delta t. And you have several pairs, several examples like that in your training data set. And you try to fit or approximate the operator that maps a source term to the corresponding solution. And here you almost have no information regarding the type of equations that govern your system. And so the idea is that you can't rely on traditional techniques for this. You have to use machine learning to incorporate the amount of data. And also another advantage is that once you have approximated your model, you can then do fast inference, so you can evaluate it extremely fast. So for instance, that's very useful in applications like weather forecasting, where you want your computational time to be slower, to be faster than the prediction time. So if you try to predict the weather 1 hour later, you want your computation to take less than 1 hour, otherwise the application is less. And if you want to embed this kind of applications in other tasks, so if you want to do design optimization in engineering, these kind of techniques are also very helpful there. So if you are interested in operator learning, there are 2 recent surveys. So the first one is the one that we wrote that has more like a linear algebra flavor, and I will come back to that to understand and motivate new deep learning architectures for addressing this problem. And the second one has more by a group in Caltech, has an approximation theory flavor to understand what the size of the neural networks needed to approximate these problems. Okay, so our aim in operator learning is that we assume that our system is governed by an unknown partial differential equations of the form L of u equals F. So L here can be a Poisson equation, Navier-Stokes equations, etc. But I don't know what L is. So L is a differential operator, it's unknown, so I don't have access to it. And the idea is that we are given pairs of source terms F and solutions U, and we try to approximate the inverse operator that takes in source term F and maps it to U. So as an example, if you have, for instance, a beam and you compress it, Your source terms might be the compression force that you apply on the right hand of the beam, and the solution U can be the displacement, so the observed displacement of the beam structure. If you are looking at time-dependent problems, for instance, fluid velocity problems, your source terms can be your initial condition of your fluid flow, and the solution can be the corresponding fluid velocity in a longer time. And so we essentially collect those pairs of data, of training data, so F and U, either through experiments, so we do a concrete physical experiments in the lab, or we use a legacy numerical solver, or we use a numerical solver to collect those. And then there is an expensive step which consists of training the neural network here. So it's a specific type of neural network, and we'll come back to this later, that takes in the function F and outputs the solution. So we do a training step here, a training process here. So we train our neural networks on a training data set of pairs F and U. So this is quite expensive to do. And the idea is that once you have trained your neural network, you can make fast inference, and you can evaluate it at new source terms to make fast inference. And in principle, this is much faster than existing numerical solvers. But the main application is when you don't know the problem, the equations, so you can't use existing numerical solvers. And so there are many different architectures, so neural network architectures that have been proposed to do this step, so to approximate this inverse operator, so this operator that maps source to solution. So the first one is the definite. That was one of the first papers that introduced the field of operator learning, which is based on a branch and truncation network. So this is kind of performing a low-rank approximation of this solution operator. The second one is the Fourier neural operator, which is based on the fast Fourier transform and convolutional neural networks. So this is similar to spectral methods, if you have heard about this in numerical analysis in most of us. And the last one is the deep green approach. It's based on a autoencoder architecture. So there are many approaches that have been, many architectures that have been proposed that try to exploit all the recent advances in machine learning. So you also find transformer-based architectures in this work here. But so all these approaches essentially address the same tasks. They try to approximate the solution operator, and they just differ based on the type of architecture that is. So key question is to understand what architecture is better for different types of problems. So I'm just going to show you a quick example on with a Jupyter notebook on how we train the Fourier neural operator in practice and how it looks like. Okay, so I hope everyone can see this. I can make it even bigger. So this should be fine, I think. So the aim, just hiding this. Okay, so the aim in this example is that we have a system that is governed by Darcy's law here. This is this system here. So it's a very simple equation where we have a diffusion coefficient A of xy that governs the diffusion phenomenon across the spatial domain. And we have the corresponding solution U of xy here. So for every coefficient field A, I have a corresponding solution U that satisfies this equation. And so someone, the people who created the FNO, simulated a lot, this equation for a lot of coefficients A of xy. So they generated many random functions A of xy, acquired the corresponding solution U of xy, and then make a data set out of this. And so the data set is essentially a number of pairs of the form A, U, where A is essentially an image of the diffusion coefficient. So it's the diffusion coefficient evaluated on a uniform grid, 32 by 32. So you can think of it as a 32 times 32 image. And the same for U, for the velocity. So you generate random function from a distribution, from your preferred distribution, and then you do numerical simulation. So this is very easy. It's a very easy equation to solve. You compute the solution U, and then you put 1,000 of these examples in a data set. And then you do some splitting. You have a test data set, a training data set. We're going to train our neural network on the training data set and evaluate it on the test data set. And so I'm relying on this neural operator library here, developed by the authors of the Fourier neural operator paper. There are several other codes available, but the community hasn't set up yet on a common framework for addressing this problem. So it's still developing and still moving very fast. So we begin by importing. So we are going to implement our models using PyTorch. So we begin by importing the library here and the function that we need to define our models. Then what I do is I load my data set here. So it's 1,000 pairs F and U for the training of resolution 32 by 32. And then here I define the Fourier neural operator. So I'm not going to go into too much details in what gets into the model. I'm going to show you quickly what it is, but it's essentially a lot of mathematical operations like convolutions, fast Fourier transform, etc., that has been devised by the people in the by the authors of the Fourier neural operator paper. But there are a lot of different architectures here are possible. So now we define the optimizer. So we're going to use Adam W for training a model. And the loss function. So in this case, we're going to use an H1 loss function. It means that we are going to penalize both the L2 norm of the error as well as the norm of the gradient of the functions. And so because we output functions, we can train our models with different loss functions to enforce extra regularity on the model. So this is using an H1 loss function is kind of adding a regularization term to promote regularity of the corresponding solution. Because we know, because we are looking at a given partial differential equation, so like most machine learning applications, we have a lot more mathematical information regarding the problem. So we know that for certain types of input through terms F, the corresponding solution U will have certain types of regularity of smoothness, so very smooth functions. And we can try to promote that in the optimization process to get nicer solution or get better rate of convergence, etc. So this is what the model looks like. So you see it's a simpler model because it doesn't have many parameters, but the succession of kind of complicated operations. You find this spectral convolution here. These are the Fourier transform. So it's equivalent to a convolution. And it's a solution of convolution and fully connected layers. Okay, and now we can define the training, the trainer that will take our input data as batches, and we will train it for 20 epochs, for a small number of epochs, and plot the output to see what the output looks like. So here I'm training it. So this I'm talking with time x per epoch, as well as a loss function here across the training data set. And we see that our training loss function at the end has decreased from 0.7 to 0.14. Of course, I've only used a very small number of epochs, only training for much longer. But it's already sufficient to plot what the error is, or to plot the corresponding, to make some prediction on the test data set.
So now I'm going to load a few examples in the test data set and evaluate the model at unseen examples at models that add samples that it hasn't seen during training. So this is what we have. So this is our input solution. So in this case, we use a non-smooth coefficient field. So it's a random field, but it's piecewise constant. It's of this form. So this is the coefficient field A of X. Here, so it's a 32 times 32 image. Here, this is the corresponding solution, the solution corresponding to this image. And this is the prediction, the solution predicted by our model. So this is the output of our neural network. You see a pretty good prediction against the controls across different training examples. So there are some artifacts here where you can see it's not capturing all the features of the solution, but this is because we used a very small number of training epochs. Okay. Now I can come back to the presentation. So as we saw, so these architectures that have been developed work fairly well across a wide range of problems, but there are still quite a lot of unanswered questions right now in the community, and so there are questions that the community is trying to address that I want to highlight in the rest of this talk. So the first one is that not that many theoretical results right now, so I'm going to show you the state-of-the-art existing theoretical results in operator learning. They focus on different directions. And so there are questions that we might be interested to address, like trying to understand how much training data and what type of training data distribution should we use to train our model, trying to get some performance guarantees, understanding what type of neural network architectures are better suited for different type of problems, or whether the approaches that we devise are robust towards noise perturbation. And there is also some big unanswered questions in practice as well regarding interpretability of the model, because this is not a traditional machine learning task in the sense that here we are want to make prediction for applications in different fields like physics, chemistry, etc. And so there's a big question regarding trying to devise architectures and models that are interpretable. And by interpretable, I mean the neural networks, the objects that we use to approximate operators, solution operators are usually very complex. So they are very complex mathematical objects. So it's very hard to get some understanding about the system. So we might be interested in discovering dominant modes, symmetries, conservation laws, as well as singularities in operators associated with equations that we discover. So I'm now going to describe some of the state-of-the-art theoretical results in operator learning. So one of the first results that we have, and that goes back to the DeepNet paper by Liu and Al in 2021. So as you can see, the area is very recent because one of the first paper in operator learning comes from the DeepNet paper, so it's about 4 years ago now. And so this is a density result for neural operators. So neural operators are the objects that we use to approximate our system. So these are analogs of neural networks in infinite dimensions, in the sense that instead of taking as input a vector and outputting a vector like a neural network, in operator learning, we call these objects neural operators because we take as input a function and we output a function. And then, of course, we can look at how we might discretize the input functions and how we can devise architectures to discretize them. And so this theorem, so this is the universal approximation theorem for operators. So you may have heard of the universal approximation theorem for neural networks. So this is very similar to this result. So it's due by Chen and Liu and Al. And this simply says that if you have an operator between a nonlinear operator between some function spaces, then you can approximate it by a neural operator, by a one-layer neural operator, with a branch network here and a two-mutation network, so by kind of a lower, can perform kind of a lower approximation of your nonlinear operator. And this in particular tells you it's an existence type of result, so it doesn't tell you how you might find the parameters in your neural networks or how many parameters you might need to approximate this G within epsilon. Another type of results that we have are what I call entropy or asymptotic results for neural operators. And these are, again, very similar to the results that have been devised for the approximation of smooth functions by neural networks pioneered by Elgarsky and Garotsky in 2016, 2017, which is kind of a refinement of the universal approximation theorem I showed in the slide before. And that tells you that if you have a smooth operator with some nice property, like for instance, Lipschitz is continuous, so if you refine slightly the assumption that you have on this operator, or the information that you get regarding its mathematical properties, then you can construct a neural network that approximates it with an arbitrary precision epsilon, and you can get some interesting bounds regarding the size of the neural network that is needed to approximate. You have some asymptotic bounds that tells you how the complexity of your neural network should scale if you want to approximate your function within arbitrary precision. And so this you can do this kind of result for different class of operators depending on the assumptions that you make, and understand the number of parameters in the neural networks that you make. Okay, another side as well is because we are looking at, we have functions as input and output data. There also been some interesting works in trying to understand the effect of discretization errors. So how we might approximate the input and output functions, and in particular, whether we can evaluate our networks trained at one resolution to another resolution, to another spatial resolution. So there are some nice work by Sid Mishra from ETH, which tells you that if you train a neural network or neural operator to approximate an operator at a given spatial resolution, like 50 by 50, like for instance, a grid of 50 by 50, then you can try to extrapolate and to evaluate these operators when it's trained at a higher or finer resolutions. And there are some works that try to understand this behavior. In particular, you can design stable networks which have nice property in the sense that if you train it at a given resolution, spatial resolution here, then when you extrapolate forward and evaluate it at a finer resolution, you don't increase your testing error when you refine the resolution. And this is kind of a very remarkable properties of certain neural operator architectures that preserve some structure, that are designed to preserve some spatial structures of the partial difference. And so I'm interested in the link between operator learning and numerical linear algebra to essentially motivate how we might design new architectures or why certain architectures have been proposed. And so, as I said, so we consider neural operators, which can also be defined as compositions of integral operators and nonlinear activation functions. So this is a kind of a one-layer neural operator. And as you can see, this is very similar to a neural network in the sense that here, instead of having a multiplication by a weight matrix of inputs, you have a convolution with an integral kernel K. And instead of adding a bias vector here, you add a bias function. So this, in the sense, is you take a neural network and you extend its dimension to infinity, and you obtain this kind of objects. So these are the right generalization of a neural network in infinite dimensions. So you can work with functions instead of working with input vectors. And so the idea is that once we have this framework here of viewing
neural operators as succession of integral operators. Then we can study the link between the property of the given partial differential equation that you want to approximate. So for instance, whether it has periodic boundary conditions, some sort of localized behavior, whether it's dominated by diffusion phenomena, and the corresponding neural operator that have been proposed to enforce those constraints. So for instance, here the Fourier neural operator that I mentioned before enforce the fact that you're looking at a PD with periodic boundary conditions and constant positions. If you are trying to preserve localized behavior, so local effect, information only travels locally, then you might use a graph neural operator. Or if you have elliptic equations, you might be interested in the multiple G-nodes. So those are all historic architectures that have been proposed in the past 5 years. And if we look at the corresponding properties of the kernel structure K here, K is a kernel, two-dimensional kernel, these properties and these neural operators, we can, if you look at it with a numerical linear algebra approach, we can see that these all corresponds to a certain structure that we enforced on this kernel K. In particular, the deponent enforces a low-rank structure. The Fourier neural operator enforces a seculant metric structure on the discretized kernel. Graph neural operator looks at banded matrices, and the multiple GNO is looking at hierarchical low-rank approximation. So all the approach that we take is that all the architectures that have been proposed so far, if we look at a one-layer simplification, they all correspond to a certain type of metric structure. And so this, we can go from the class of PD that we are interested in approximating to looking at some PD analysis, trying to derive some interesting property for the corresponding solution operator, and derive some corresponding metric structure that motivates the development of new architectures. So if we have a certain type of or a certain class of matrices, this should naturally give rise to a new neural operator architectures that will preserve the corresponding properties of the PD. And so this in particular motivates numerical linear algebra research on matrix recovery problems and infinite-dimensional numerical linear algebra. So there have been some interesting work by Alikas and Thompson who looked at, given a matrix in a certain class, how many matrix vector products do I need to approximate it? And so we can transport this type of results in infinite dimensions to look at sample complexity estimates for operator learning. And so this is kind of what I will describe in the last part of this talk. So the last theoretical property or theoretical guarantees for operator learning that I want to highlight is the fact that we don't need much training data to approximate, to train those operators, those neural operators. And so to see that, I'm going to replicate an experiment that has been done in the literature, and that goes back to the original deponent paper by Liu and Al, where I'm looking at a simple two-dimensional Poisson equation. I'm generating some data, and I vary the size of my training data set. I train my neural operator for different sizes of my training data set, and I report the corresponding testing error. So each point in this diagram is one experiment that I did where I retrained my network from scratch and printed the corresponding error. And so I'm combining three approaches, so the Fourier neural operator, the deponent, and another one that we worked on as well. So what you can see is that there are essentially two regimes in this diagram here. The first is you see a very fast exponential decay of the testing error, where you rapidly reach something like 5% error on your data set, and then kind of a plateau due to discretization error and optimization error. And so this kind of diagram naturally gives rise to the question to understand how much training data do we need to learn a partial differential equation. And based on this experiment, it appears that unlike most machine learning applications, like natural language processing, for instance, we don't need much data to approximate solution operators of PD. This is something where people in the community have tried to address to understand this question. And so we're going to look at
differential equations, linear differential equation of the form L of u equals f, for which we know that the solution operator can be written as a Green's function, so as this simple integral operator. And so you have this type of properties, for instance, if you look at Poisson equation in this form, or the Helmholtz equation here. And you can, if you look at the Green function G, which has twice the dimension of your original input, you can read certain properties of your differential operator on the Green function. So the fact that it's symmetric, for instance, capture the fact that the original partial differential operator is etc. And so we are going to approximate this Green function G and trying to understand how much data do we need to approximate it to get some theoretical bounds on sample complexity in operator. And so we're going to consider elliptic equations in 3 dimensions in this form. So this essentially captures diffusion phenomena. So this is like a Poisson equation, if you want. We know that for these equations, there exists a Green function so that the solution operator can be written as this integral operator. And the idea is that if you approximate G, then you already know your operator, so you can make forecasting, you can make predictions at new source term by just evaluating this integral. So our main theorem states that there exists a randomized algorithm that achieves exponential convergence for learning the Green function with respect to the number of pairs fj and uj with very high probability of success. And so why is this a randomized algorithm? So the idea is that we're going to use random functions f to probe our system, acquire the solution, and exploit this information, these pairs fj and uj, to devise an algorithm that converges extremely fast to the Green function with theoretical guarantees. And I'm going briefly to go over some of the proof techniques because they exploit some information that we get, that we have from PD analysis, and then motivate new neural network architectures at the end. And so the techniques that we use are based on core techniques in numerical linear algebra that I described earlier. So we generalize them to infinite dimensions so that instead of working with matrices or trying to approximate matrices for matrix vector product, we try to approximate integral operators from convolutions with random functions f. So we are going to use the randomized SVD and techniques called a technique called hierarchical matrices. So the randomized SVD is a core techniques in numerical linear algebra. So it has been proposed in a landmark paper by Alcor, Martinson, and Trop. So if you have a matrix A, first we know that there exists a singular value decomposition to A from U sigma V star, where U and V are orthonormal matrices, and sigma contains the singular values of A in decreasing order. And so the Eckhart-Young theorem tells us that the best Rankine approximation error is given by the tail of the singular values. And so the randomized SVD is a landmark algorithm that says if you have a black box matrix A, and I can only access it through matrix vector product. So think of it as a streaming model. So if your matrix is extremely large, you cannot access it, you cannot store it manually. So if you have a black box matrix A that you can only access through matrix vector product, then the randomized SVD tells you that you can construct a very good approximation to it, just using a small number of products with input vectors. And you have very nice theoretical bounds that behave like this, that are just a tiny bit worse than the best approximation error you can do, which is given by this epsilon k factor here, by the tail of the singular values of the matrix. And so we can simply generalize this idea in infinite dimensions, where we look at the proofs and the theorems, and we grow the dimensions to make sense of this algorithm in infinite dimension, in the sense that now, instead of trying to approximate the black box matrix A or matrix vector products with random function F, random vectors F, we try to approximate an integral operators from convolution with random functions F here, sampled from a Gaussian process. And we have essentially the same theoretical arguments, theoretical results that gives us guarantees on the approximation error of the randomized SVD in infinite dimensions. So we are something like tiny bit worse than the best approximation error you can do, which is given by this epsilon k factor here. And so now we can apply these results directly to Green's functions to try to derive a sample complexity result. So we apply these bounds, so we try to approximate Green's function. And if I manage to bound this epsilon k factor here, then I'm done, and I prove that we can converge to it very fast. So now I need to understand essentially this epsilon k factor, how well it behaves and how well it decays as I used k input functions to approximate G. And the issue that we have is that the Green functions are not smooth around the diagonal. And in particular, this implies that this epsilon k factor decays very slowly with k. So what we really want to prove our theorem is that we want to see an exponential decay of this bound with respect to k. So k is the number of data that I use. And we want this number term on the right to decay exponentially fast as I increase my number of input and output data k. And so to do that, we're going to exploit another technique from PD analysis and looking at regularity of the corresponding solution, which is a lowering structure away from well-separated elements. So if you have a solution to these type of equations, diffusion problems, we know that most of the information travel locally, in the sense that if you take 2 points in your solution that are very far apart in the spatial domains, there is a very low correlation between those, and you can approximate those interactions globally away from the diagonal by a lower. You can do a lowering approximation of these interactions. So as an example, so we take our spatial domains. So this is the domain for the Green function. If you are 2 points that are close together, you are basically belonging along the diagonal of the Green function. So the diagonal simulates points in the solution in the spatial domains that are close to each other, while all the Green parts away from the diagonal simulates points that are far from each other at one side to the domain. Look, this essentially captures interactions from one side of the domain to the other side of the domain. And so these results from Bernard van Haagbusch in particular tells us that each of these Green blocks in the Green function can be well approximated by a lowering approximation. In particular, this epsilon k factor restricted to this Green block is very small and decays exponentially fast with k. And so what we can do is we can refine our algorithm where we exploit this hierarchical structure to first approximate the Green function away from the diagonal on these Green blocks, and then exploit this information progressively as we go down the level to capture all the Green blocks which captures the long-range interaction. And to look at the diagonal, we can essentially exploit other results regarding how well the Green function decay away from the diagonal. And this tells you in particular how many levels in this hierarchical partition of this solution operator we have. And so we essentially approximate all the Lagrange blocks in Green with the randomized SVD within epsilon. And then we refine until the diagonal has norms smaller than epsilon. And if we combine all of this together, this gives us a scheme that converges exponentially fast to the Green function and answers in particular the question posed by the experiments that I showed earlier, which is why do we need so little amount of data to approximate the solution operator? And so this theoretical argument is kind of a hierarchical partition, so hierarchical structure. In particular, it does an approximation of the solution operators at multiple scales in the domains. And we are going to use that to define a new architecture inspired by this theoretical result. And so this is a joint work with a recent joint work with Nassim Bouzani, who used to be a postdoc here in IX and has now joined Amazon recently. And so we propose a new architecture which we call structure preserving operator learning that exploits both the multi-scale nature of partial differential equations. So we have this kind of approach, the multi-grid approach, where we take in the solutions on a fine grid and then approximate the behavior on coarser and coarser grids. We have this kind of V-cycle approach or multi-grid based approach, if you're familiar with it. And we used a finite element encoder decoder. So we use a finite element approximation of this input and output functions so that we can control the mathematical spaces in which they belong, and so that we can enforce some specific properties of the solution operators, like boundary conditions exactly, for instance, which is very difficult to do with current modern, with state-of-the-art approaches in operator. And so the paper will appear in archive in 1 or 2 days. We are just wrapping it up right now. And so as a conclusion, so we saw that there's lots of work right now happening in operator learning. And so we can exploit knowledge from numerical analysis, numerical linear algebra, to motivate and design new neural operator architectures. This also can help us to understand the current approaches that have been proposed better, so getting some theoretical bonds. There's still a lot of work to be done in this area. And some areas that is yet mostly unexplored in operator learning, which is trying to derive, enforce some interpretability and derive new architectures that we can interpret, and that gives us some intuition regarding the learning process. And with that, I'll conclude, and thank you for your attention.
Questions?
So, what kind of like operators you have in general, like say analyzed? More likely the let's say the underlying is, or what are the simplest and most complicated cases?
So the simplest case are problems, for instance, fluid dynamics. So the state of like a normal benchmark would be like looking at Navier-Stokes equations, trying to predict the solutions in time. And the state-of-the-art, most complex applications that I've seen so far is the papers by DeepMind or NVIDIA on weather forecasting. So those are unreachable applications for us in academia, I think I would say, where they partner with like major weather forecasting centers and have huge training computations.
You know, are they work on like quantum, say, scattering operators for its matrix, like in quantum field theory or say relativistic field?
I don't know. I've seen mostly applications in fluid dynamics or engineering, material designs. Quantum computing, I'm not familiar. I'm not sure.
Yeah, because it seems quite a lot of harder to go into some like quantum field theory and like particle physics. Because these are more like classical fields, right?
Right. Yeah.
With the so it looks like you've got the most theoretical results for the elliptic case.
Yeah.
How does that change with time dependence? Because then, you know, at long times, then they are all correlated to this hierarchical structure initially. But
right. So we also have like a paper on the parabolic case, which works very similarly than the elliptic case. So it's time dependent, and you also have like a low correlation as time goes because it's mostly diffusive in time. It gets much more difficult if you are looking at hyperbolic equations like wave equations, because now you get correlations back in time as well. So if you're looking at wave problems, the wave bounces back across the boundary. And so now instead of having this nice diagonal structure of the integral operator, you have a much more complicated structure. You don't know what the structure is exactly. And so you have to test for it or something like that, because now this could be like a kind of a losange type here, where the singularities locations are unknown. So there's one paper that look at the 1D case, but in higher dimensions, there's no work right now. And there's also, some interesting questions on how we would detect even where the singularity lies for the hyperbolic case. And of course, this is all linear, so non-linear is still even even beyond right now. But
is it easier with hyperbolic stuff to try and discover it and how specifically?
yeah, so I think the
Just-
1D paper, what they do is they use this kind of the same numerical linear algebra idea. They try to essentially discover this pattern here on the fly, in the sense that they do a partition. They test whether the object that they got is low rank, and if it is, if it's not, then they refine along this direction. They kind of combine these ideas with like discovering where singularity is on the fly. In
So
the
like AMR, but in some weird space.
yeah.
Do you think that it will always be more efficient than forward problem? I suppose you're saying like you only have data. But...
What do you mean by forward problems?
No, I've just answered my own question in my head. Ignore me.
But yeah, so these theoretical guarantees, yeah, so they are based on classical algorithms. So they don't actually say something about the neural operators itself. This kind of results say something more like, if you look at the class of elliptic problems, you should, if you try to use it to approximate it with like a neural network, you should aim to achieve good accuracy because we know it's possible for this class of problem. This kind of gives us a kind of a bound that you should try to aim with your method, but it doesn't say exactly, it doesn't say your neural network technique will achieve this accuracy. You just say, essentially, I'm just saying that a class of elliptic problem is easy because we don't need much data to approximate. And this is all exploiting smoothness ideas. So there's some hope that the same ideas work for nonlinear problems, but yeah, maybe in a few years, come back to talk about it, but not now.